So I work in the School of Psychology. I work in the School of Psychology, but I don't primarily teach psychology. I teach research methods and I teach statistics. And a lot of students don't particularly enjoy this. And so what I've been trying to do, working with my colleague Nikki Dean Marshall, is we've been trying to find out how to improve the teaching of statistics. Now, you're all able to see the title, the main insight that I put on at the front, the idea being the recommendation that we're studying to see if it works. We want to see if it would help to begin with an example. This is a silly example, the heights of aliens. Then you give students some data, and then you show them the equation last, building up from concrete up to abstract. I'm going to begin by talking about the importance of statistics. But what is statistics? Well, it's an epistemology. What does that mean? Well, what I mean by that is that people make the mistake of thinking that statistics is math. It's about long, boring equations, or that statistics is a its own how do you describe it? As if it's just a set of tools to be used in a small amount of research circumstances. That's not the case at all. Statistics is an epistemology, and what that means is that it is a way to understand and make sense of the world. So if you want to find out why people get anxious or have high blood pressure, or why the stock market collapses one day, it doesn't happen because of one reason. All of these phenomena are happening for many, many different reasons, and every time you measure it, it gives you a different answer. And so you have all this measurement error and all these too many causes hitting into each other. These things are chaotic. And statistics is the process of deriving knowledge despite chaos. Turns out that your students, if you're really teaching any scientific subject, are going to need to learn about statistics. That includes technology, that's like computer sciences and healthcare and law, economics, and also psychology. That's in bold, because that's the subject that I'm teaching on. There are, however, two challenges, two central difficulties in teaching statistics. The first one is difficulty understanding it. It turns out that across different ages, people have difficulty understanding even the, let's say, the most threshold ideas in statistics, like the average and spread away from the average. And also there are common misunderstandings of statistics across different ages. So one of them is the mistake of people using counts instead of proportions. Which town should you live in? Should you live in town number 1 or town number 2? Well, town number 1 has 10 burglaries. Town number 2 has 20 burglaries. Like, so obviously you'd go to town number 1. But maybe, and this is the part that people don't tend to ignore, maybe town number 2 has 10 times more people. So the burglaries are spread across more people, so you'd actually be safer there. That's a mistake that people tend to make. Another one is called equiprobability bias, the mistake of thinking that everything is equally likely. And just as likely to get hit by lightning as not. That's a misunderstanding of statistics, right? Because there's two outcomes, so you think they'd be equally likely. Here's another one. This is called the law of small numbers. In statistics, there is actually something called the law of large numbers, which is basically the more observations you have, the closer you get to the real answer. The law of small numbers is a mistake. It's the mistake of thinking that your small number of limited experiences is representative. So maybe someone who's once eaten some Chinese food, and that made the person feel sick, and therefore vowed never, ever, 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 ever to eat any Chinese food again because all of it must make me sick. The mistake of thinking, how did that person possibly win the election? I have 20 friends and none of them voted for him. That's a mistake. So people have difficulty understanding the statistics. And that last mistake is the mistake of underestimating differences between measurements, differences between samples. It's no wonder that people don't like things, that they have a difficult time understanding. Another difficulty is statistics anxiety, a sense of tension, worry, apprehension caused by exposure to statistics. Leads to procrastination, it reduces academic performance, especially if you have less experience in statistics, and especially if you don't think that statistics is useful, because you could imagine that if you really think that the statistics is useful, that motivation is going to take the edge off the anxiety. I love it when academic articles become a bit, how would you describe it, melodramatic. This is one essay about statistics education which described it as one of the dreaded courses. Isn't that wonderful? I wish I could write more like that in many of my essays. Okay, well, how do you teach statistics? Well, how do you teach anything? Let's find out. One idea of teaching is the traditional model, which is that you are the teacher and I am the student, and you tell me things, and I am less a person than I am an empty barrel which is to be filled with facts. That's the traditional model. I just tell you things. The reason why the university, by the way, has a position called a reader is because back in hundreds of years ago in the Renaissance, the job of the teacher was just, because the teacher was the only person who could read, was just to read the book and you would listen. It's completely passive. That's not how people learn. If psychology teaches us anything, it's that people instead learn, that's right, in accordance with the constructivist model. I'm the student, you're the teacher, I already know a bunch of things. I already know a bunch of things. A jigsaw of knowledge. And so when I learn something, when you tell me something, what I do is I translate that thing into the jigsaw and through mental action, add it to what I already know. When you learned division when you were in school, you didn't learn how to divide because the teacher wrote A equals B over C, which is the formula for division. That's not how you learn to divide, because that doesn't mean anything yet. What happened is the teacher said, you know what a pizza is? Yes. Do you know what 4 is? Yes. Do you know what 6 is and 8 and all these numbers? Do you know what sharing is? Okay, you know about sharing. Well, imagine sharing a pizza. You have so many slices shared across people. The reason you can get abstract understanding is because you take many examples in the real world and you reduce them, you simplify them, you abstract them. It's the same reason why you write the abstract at the end of writing an academic paper. So you go from concrete to abstract. So what's the recommendations for teaching statistics? Well, the good news here is that some of the early statistics education researchers were also researching, well, education in general. They were studying this constructivist model. What we're seeing here is Jean Piaget, developmental psychologist, and also his collaborator Barbel Inhelder. And the recommendation is that teaching should be active, using worked examples, calculations to get students to do statistics, and it should be concrete, using real data, real examples. The problem is often that's not how statistics is taught. How it's often taught instead is that the lecturer gives you many equations, so let's say 50 minutes straight, and then at the end maybe you get a little bit of homework to do a calculation at the end of it. The opposite of what it should be. Well, how would you make statistics concrete? Well, to some degree it has to be abstract because it involves math, and math is abstract. And what I mean is that 2 plus 2 is 4, even if it's not 4 of anything, which is a strange idea. It's almost like it exists beyond the experience. And also, statistics is about probability. It's about what would happen if an idea was true, about a hypothesis. A hypothesis is hypothetical. A hypothetical thing is abstract. You need to imagine all the things that could happen if a particular idea was true. Let's imagine this. Show of hands. Anyone here ever played Monopoly? So some of you played Monopoly. So what happens when you play Monopoly is you have 2 dice and you roll the dice. And let's say you get a 5 and you get a 7. Well, you can't get a 7 because it's a 6-sided dice. You get a 5 and a 2. That's when the reason why you get a 7 is you get a 5 and a 2. You add those together and then you move 7. That's the rule in Monopoly. And so I could ask you, what is the probability of you getting a 7? Well, that's a hard question, because in order to answer that question, you need to imagine all the things that could happen with the first dice and all the things that could happen on the second dice. There's 36 possibilities, 6 of them give you a 7. You need to calculate all the possible things that could potentially happen, and you need to imagine that, and that's abstract. So no wonder it's hard. The good news is that statistics is always concrete in the sense that it's always numbers in a particular context. It's not just 2 plus 2 equals 4. It's always 2 of something plus 2 of something equals 4 of something. So it's always concrete, grounded in the real world. And so that, to some degree, makes statistics easier than math, because you can always ground it in real world examples and don't have to skip it and just go to the abstract stuff. So you should use physical and concrete examples. The problem is that that only tends to be done after you've given people the abstract information. But then it's also not clear what kind of examples to give. So one thing you could do is you could give real world examples. Data from the UN, for example. And that shows that it's actually useful in the real world. So it makes it relevant in the real world. Maybe it makes you less anxious because, look, I've analyzed this real data set. Problem is that real world data can be messy, it can be distracting. A lot of people don't give their data. A lot of people miss a few items. You give outliers, maybe you have a lot of careless responses. But what can you do instead? Instead, you could try artificial, fake, simulated data. Do a little coding in RStudio or Python, make up some data, which is good. It's neat and tidy, and you can use it for examples. And you can make it a funny example as well. You can make it humorous. That can improve learning and reduce anxiety. But you don't want it to be distracting in the humor. Problem is with using an artificial example, is that it's hard to convince someone that statistics is useful in the real world if you're giving them examples which you literally just made up in the computer. It undermines the point. So what I wanted to find out is, will the order equation first or equation last and the type of example affect statistics anxiety and understanding? So what I've got is two IVs, two predictors, order and examples, to see if they predict those outcomes of anxiety and understanding, if those two things can help us to overcome the barriers in teaching statistics. What we did is we collected data from Sonar. Show of hands, anyone else saw what I mean by Sonar? Sonar is a website which psychology students use. They can participate in studies, and then they get some points. And if they get enough points, it means that they can then use that website in order to collect participants from their own undergraduate degree. So it's a website that allows you to get participants online. And we collected data from both Nottingham and Sheffield Hallam University. Participants had to be 18 years of age or older, fluent in English, normal or corrected to normal vision, for example, with glasses, and they had to have experience of Excel, because we were getting them to do some calculations in Excel. And when we did the power analysis, what that meant was that we did a statistical analysis to say that we need 128 people, otherwise we'll just get silly false negatives. So that's the amount of people we need, 128, and data collection is still ongoing. So what we did is we had two independent variables, the order. There were two levels of order. Either the person saw the equation first, so the participant goes onto the survey and then they see a text page with this big equation. It was an equation for standard deviation in statistics. Standard deviation is a measure of how far numbers are spread from the average. And they have the text page which explains the equation. And they also have another section which gives an example. And in the example section, there's a data set which they can download. And then it goes through some screenshots explaining in Excel how to calculate one variable, how to calculate the standard deviation of one variable. And then participants have to follow through those instructions to calculate the standard deviation of the other one. So everyone sees the equation, everyone sees the example, but there's also two kinds of example. There could be a real life example. This is life expectancy, data that I got from the United Nations, or the fun, silly example, which is the height of aliens. And it says, look, those aliens, the red ones, they're called rolls, and that helps them to roll. And those big blue ones, they're called movals because they have big legs which help them move. And it's kind of just a silly example, but it's rather intuitive and everyone can understand it. And the dependent variables, statistics anxiety, was measured with the STARS, Statistics Anxiety Rating Scale. That's a validated psychological measure. It's valid, it's reliable. And then for understanding of statistics, so all of this was about understanding of standard deviation. What we did was we created a quiz domestic understanding of standard deviation, which was based on the information which we provided in both the equation and the example. And by the way, it was the exact same information about standard deviation in all of them. And so the amount of information was actually the same across all the different conditions. The only thing that changed was the order and the content of the example. This is what the study would look like from the point of view of the participant. First, you do the ethics forms, the information sheet and the consent form. And then you enter some demographic variables. And then everyone is randomly allocated to one of four conditions. Either you see the equation first or you see the example first. And within the example, either you see the real example or you see the fun example. And then after that, everyone's brought back together, completes the statistics anxiety measure, after which they complete the understanding of standard deviation measure, after which they then complete the debrief. The reason why we asked them to do the anxiety measure before the understanding measure is because we didn't want their score on understanding to bias their result on anxiety, because you could imagine if someone scores poorly on the understanding measure, that might increase their level of anxiety. So we did the anxiety measure first. Data collection is currently ongoing. So far, we have data from 45 participants. This is what it looks like. Not very intuitive. It also looks like this. What we're seeing here on this box plot is we're seeing the level of statistics anxiety across all four different conditions. EQ means equation first, EX means example first. So that is the level of statistics anxiety across all four different conditions. And as well as that, we have level of understanding across all different conditions. If you look at these box plots, you will see two things. The first thing you will notice is they're all very wide. And the reason why they're wide, they have a lot of error, is because we haven't measured enough people yet, because data collection is still ongoing. This is just descriptive statistics. I'm not doing any statistical tests on it yet. The other thing you'll notice is that the averages are almost all the same, which perhaps they are all the same, or perhaps that's just a result of the fact we haven't measured enough people, and that gives us false negatives. Like I said, we're going to need to collect data from 128 people. Data collection is still ongoing. What I'm going to show you now is what we're expecting the data to look like in the end. We expect that there will be an effect of order, that it will look like this. The participants who see the equation first will be higher in anxiety and will be lower in understanding. Basically, we predict that participants who see the equation last will do better, less anxious, more understanding, will do better than participants who saw the equation first. I expect there'll be some effect of the example used. I'm not sure what that would be, and as such, I haven't put it in the diagram. So that's what we're expecting. And if that is the case, if we see that result, what it means is that it would then be best to save the equations last, restructure the way that the material is taught in the lectures, giving worked examples before the equation. What happens conversely, you may ask, if all of those lines are about the same average? What if the order and the example makes no difference whatsoever? Will I be upset about this? No, I will not. I will not. And the reason for that is because if those things don't make a difference, what it means is that all of these teaching techniques are equally effective, which is good news. And then what I would then do is go to find something else instead that would help students. And so it's a good situation either way. And so data collection is still ongoing. Nevertheless, this is what we predict based on the existing literature. What we have here is the references section. Sometimes people end the presentation by going click, 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 click. Here's the 50 references you can't read. If you want to see the references, you can just go on the QR code. There's my contact information if you would like to contact me. What I also do is I have a YouTube channel in which I talk about a bit of psychology, but I also talk about quite a lot of statistics. You can see that there. And I also have a statistics resource called Statistics Launchpad, which is being used widely across the university. It's being used in School of Biosciences and Biotechnology and in the Malaysia campus and so on. So the main message is that this data is currently being collected. And when the analysis is over, hopefully we'll be able to find out how best to improve students' understanding of statistics so that they can do better in their courses and they can use numbers to make sense of the world.